When last we talked, we covered what makes a sound argument a valid argument. Today we're going to continue with fallacies. A fallacy is an error in reasoning that results in an invalid argument. Three common fallacies are using ambiguous premises, circular reasoning, and jumping to a conclusion. We can show an argument is invalid by constructing a truth table. If there is a critical row that has a false conclusion, then the argument is invalid. We showed the last time the truth tables and the what makes a critical row. Another way to find an argument of the same form is to find an argument of the same form with true premises and a false conclusion. So, as an example of that, there's converse error. Okay, take this statement. If Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. This takes the general form P, then Q, Q, therefore P. Now this looks similar to the modus ponens syllogism, but in fact it is not. It is an invalid argument. Not all people that sit in the back row are cheaters. So if Zeke sits in the back row, Zeke is a cheater. That may be true. Or no, if he's a cheater, then he sits in the back row. That may be true. If Zeke sits in the back row is also true, but it may not be true that he's a cheater. That has not been established. So this is not modus ponens. It is the converse. Modus ponens, if you recall, let me make sure I get it right here. Modus ponens is if P then Q, and P then Q, therefore Q. It is the converse of that. Okay? Now, then there's the inverse error. Where the inverse is used instead. Consider the following argument. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore, these two vertices have the same color. This has the form P, if P then Q, not P, therefore, not Q. Now, modus tollens is P, if P then Q, and not Q, therefore, not P, right? Not P. I get ponens and tollens mixed up sometimes. This is modus tollens. It's the inverse of that. The not Q, instead of, it should be not Q, then not P, for it to be a valid argument. This is valid. This is not valid. So if in the example statement, therefore these two vertices have the same color, they could have different colors even though they are not adjacent. It's kind of like on a map, the different states are, if adjacent states have different colors, well, two non-adjacent states can have different colors as well. So then there's the argument, an argument with a false premise. If a premise of an argument is false, then the argument is invalid, even if it is a valid argument form. So, take the argument, if Canada is north of the United States, then the temperatures in Canada never rise above freezing. Canada is north of the United States, therefore the temperatures in Canada never rise above freezing. That is the P, then Q, P, therefore Q, which is modus ponens, again. It's a valid form. Oh, oops. The form is valid. But the first premise is false. If this is false, then the argument is not valid. So an argument is sound if the form is valid and all its premises are true. And of course, if the argument is not sound, then it is called unsound. Kind of a gimme there. But it has to have a valid form, and all the premises must be true. So you look at the truth table for each of the premises and the conclusion, and make sure that all the critical rows have a true conclusion, and then the argument is sound. Now, contradictions and valid arguments. Kind of a rule here. If you can show the supposition, show P, for example, when false, leads to a contradiction, this means P is true. This can be verified using a truth table. If you have P, not P, C, and not P implies C, and P, that's true and false, false and true, false and false. Contradictions are always false. If not P implies C is true, not P implies C is false. This is your only critical row. Your premise is true. P is true at that point over here. So this is a valid argument. Not P implies a contradiction, therefore P. So if you have a large expression and the part of the expression to the right of the arrow leads to a contradiction, the inverse of what's to the right is true. So you can prove something to be true by showing that the inverse of it is a contradiction. Now, a quick summary of the rules of inference. I need my glasses for this. This is tiny writing here. Modus ponens. If P, then Q. P, therefore Q. Modus tollens. If P, then Q. Not Q. Therefore, am I getting that right? Yeah, not Q, therefore not P. Okay. Generalization. Generalization has two forms. If P, well, just P is true, therefore P or Q is true. Specialization. If P and Q, therefore P. Elimination. If P or Q and not Q, therefore P. Transitivity. If P, then Q, and Q, then R, therefore P implies R. Then there's the division into cases. Yeah, everybody got this so far? All right. I'm sorry? Got it? All right. Division into cases. P or Q. P implies R, and Q implies R. Either P or Q is true, therefore R is true. Therefore R. And then finally, what we just covered was the contradiction rule. Where if not P implies a contradiction, therefore P. And well, that is it for that section. I'm going to go on to the next section. I don't have my notes complete for that. Computer error on my part. So I have the slides from the book that we can go by. There we go. Hopefully these slides work out right. The digital logic circuits, an application of these ands and ors. Combinations of signal bits can be transformed into other combinations of signal bits by means of various circuits. Because a variety of different technologies are used, the actual circuits depend on the technology. So we look at these logic circuits as black boxes. A black box is a way of looking at different processes. It allows you to ignore the inner workings of a process and only be concerned with the inputs and the outputs. How the wiring is done inside them is not important. What is important is what that circuit element does. Different logic circuits are represented by their common signals while the inner workings of the circuit are ignored. You have the specification of the black box by way of a input-output table, also known as a state table, that lists all the possible input signals together with the corresponding output signals. The previous slide has showed a black box symbol with 3 input signals and 1 output signal. Well, since each of these signals can be valued 1 or 0, there are 8 possible combinations of input signals. Same as how many variables there are in logic statements. The number of possible input combinations is 2 to the power of the number of input variables. One possible correspondence of input and output signals is this state table here. Given the inputs, these combinations yield those, in particular, those outputs strictly. The black boxes are typically divided up into 3 basic gates. The NOT gate, or inverter, is a circuit with 1 input signal and 1 output signal. If the input is 1, the output is 0. Likewise, if the input is 0, then the output is 1. Corresponds to the NOT logic function that we've been using so far this semester. The AND gate is a circuit with 2 input signals and 1 output signal. If both inputs are 1, then the output is 1. Otherwise, the output is 0. The OR gate is like the OR function we've been studying. 2 inputs, 1 output. If either input is 1, then the output is 1. If both inputs are 0, then the output is 0. Those are the symbols and the state tables for those gates. For those of you who have had digital logic, this is old news for you. but they are the same tables as the not, and or of the logic operators that we've been using thus far. Rules for a combinational circuit. Never combine two input wires. A single input wire can be split part way and used as an input for two separate gates. An output wire can be used as an input, and no output of a gate can eventually feed back into that gate. Although that is common in what's called sequential circuits, which are a little bit more complex and beyond the scope of this section. Input-output table for a circuit. If you're given a set of input signals for a circuit, you can find its output by tracing it through the circuit gate by gate by gate. Let's see here. Like P through a knot ANDed with Q. P is 0, Q is 1. So here you would have a 1. The Q would be 1. 1 and 1 ANDed together would result in a 1. Here you have 3 gates. If P is 1 and Q is 0, then the OR gate would be, the result would be a 1. And then the NOT would invert it to a 0. ANDed with R being equal to 1, the result S would be 0, because 0 ANDed with 1 is 0. So we just go through that. We just went through that. And so output is, in fact, 0. Construct the input-output table for the following circuit. P ORed with not Q. You list the 4 possible inputs and trace it through, and you get that resulting input-output table, state table. Boolean expression corresponding to a circuit. In logic, variables such as P, Q, and R represent statements, and a statement can have one or only 2 truth values, true and false. Statement form is an expression such as P and the quantity not Q or R, composed of statement variables and logical connectives. Any variable, such as a statement of variable or input signal, that can only take on only one of 2 values is called a Boolean variable. An expression composed of Boolean variables and connectives is called a Boolean expression. The Boolean expressions that correspond to the circuit below P or Q and not P and Q. You work from the left to the right to create your expression, using parentheses to group things together. As you go left to right, the order of operations would indicate these are done first, so those would be in parentheses. The not would be outside the parentheses of the and then finally the outer last operation would be the and on the right. I'm going to skip this one here. But so P or Q and not P and Q. This happens to be the expression for exclusive or, either P or Q, but not both, because the and inverted takes it out of the equation. There's other ways to express the exclusive or. This just happens to be one of them. A recognizer is a circuit that outputs a 1 for exactly one particular combination of input signals and outputs zeros for all other combinations. So this is an example of a state table for a recognizer. All zeros except for the 1 here. When P and Q are 1 and R is 0, it outputs a 1. All other combinations entered into the inputs would yield a 0. The circuit corresponding to a Boolean expression. Well, strategy is to work from the outermost part of the Boolean expression to the innermost part, adding logic gates that correspond to the operations in the expression as you move from right to left in the circuit diagram. So, you have the first, the last in the order of operations. This is kind of the opposite of what we did a few minutes ago. You start with the or. Then you would have the not, Q, ORed with the and, Q, and not P. So your inverters would be, let's see here, I just did that. The not P would be, the not would invert the P into the and. The Q would be split in between the and the inverter. And these two would be ORed together at the end. To start constructing this circuit, put one AND gate. Oh, we didn't look at that one. That would be a 5-input AND gate. Finding a circuit that corresponds to a given input and output table. Now, design a circuit for the following input-output table. You have only 3 outputs that are 1. The rest are zeros. So what you do is you first construct the Boolean expression with its table as its truth table. To do this, identify each row for which the output is 1, in this case 1, 3, and 4. For each such row, construct an AND expression that produces a 1, or true, for the exact combination of input values for that row, and a 0 for all other combinations of input values. For example, row 1 is P and Q and R. The expression for row 3, this is why I don't like these slides, because they mess up periodically here, would be P and not Q, because Q is a 0, and R. So it would result in a 1 for P equals 1, Q equals 0, R equals 1. Likewise, the row for row 4 would be P and Q, not Q, and not R. So the result, then you take all these and you OR them together. If this is 1, or if this parentheses here is 1, or this parentheses, or this parentheses, is 1, then the output should be 1. And therefore, you are given, end up with this circuit. Now, this is not simplified. You could make this a little bit easier, but this would work. It would have the correct outputs given the inputs of the state table. Let's see here. Yeah. And observe that the expression is a disjunction of terms that are themselves conjunctions in which one of P or not P, P or Q or not Q, and one of R and not R all appear. Such expressions are said to be disjunctive, normal form, or sum of products. In digital logic, you'll see the term sum of products form because the symbols used in expressions in digital logic are similar in nature to mathematical symbols, and it looks like you're adding together the products of the different inputs. Therefore, it's a sum of products. Simplifying combinational circuits. Well, consider these two. If you trace through a circuit, you'll find that its input-output table is this here, which is the same for the input-output table of circuit B. Thus, these two circuits do the same job and with the same inputs and output and same outputs. So these two are equivalent. The digital logic circuits are equivalent if and only if their input-output tables are identical. And this is the same type of thing here. Use theorem 211 to show that these expressions are logically equivalent when regarded as statement forms. So you have this statement and this statement. You can use the distributive law, commutative law, the negation law, and then the identity law to simplify the expression from the mess up here to this simple P and Q down below. So this is commonly referred to as Boolean algebra. You are manipulating and changing the expressions to a more simple form. Let's see here. The circuits are equivalent, yeah. NAND and NOR gates. don't use these much in logic, though they are used in electronics quite frequently. They're useful for a variety of reasons. A NAND gate is a single gate that acts like an AND gate followed by a NOT gate. And a NOR gate acts like an OR gate followed by a NOT gate. So the NAND gate is 0 when and only when both input signals are 1, and the outputs for the NOR gate is 1 when and only when both input signals are 0. The logic symbols corresponding to these gates are the Sheffer stroke and the Pierce arrow for simple notation in logical terms. The table here shows the state tables for the NAND and NOR gates, as well as the symbols used in schematic diagrams. Notice the bubble on the NAND gate looks like a AND gate, but it has a bubble on the output, and the NOR also has that bubble on the output. That bubble means it is an inverted output. So it is an AND gate, but with a inverted output. Likewise, the NOR is an OR with an inverted output. Okay, so use the theorem to theorem 211 and the definition of a Sheffer stroke to show that not P is equal to P NAND with P. And P or Q is the NAND of P and Q and the NAND of Q and Q, or P and Q and Q. And it shows you the steps. The idempotent law for V for OR, and definition of a Sheffer stroke. And the double negation law, De Morgan's law, and definition of the Sheffer stroke. What this shows is that not P can be obtained using NAND gates. P or Q can be used with, or can be implemented using NAND gates as well. This makes a NAND gate a universal gate. You can do anything logically with a NAND gate. Just have to have the right combination of stuff. And I think that's it for that one. And we're not going to be able to get into the next slide, so next batch of slides, running short on time. But all right, that would be a wrap it up for the day. Sorry for the brief lecture and not able to get through it all. But we'll finish up on Tuesday, start in on chapter 3 as well, and then have a test on chapters 1 and 2 on Thursday. And I will get the homework due dates adjusted accordingly as soon as I get up to my office. So have a good day.